Welcome to The Explainer. Today, we are diving into something truly wild. We're going to look at how an incredibly advanced mathematical framework, the Adelic Langlands Program, can actually be used to mathematically squash an accidental anomaly in combinatorial algebra. Think of it like using the fundamental, overarching laws of physics to track down and eliminate a theoretical bug hidden deep in the universe's mathematical source code. It is an absolutely incredible story of how totally different fields of mathematics intersect to prove a single, stubborn truth.
All right, here's our game plan for today so you know exactly where we're headed. We'll kick things off by defining the Fröberg Conjecture itself. Then we'll map that out using the Adelic Langlands map. From there, we'll deliberately inject a bug into the system by modeling an accidental anomaly, watch the system react with a fatal phase obstruction, and then use 4 distinct mathematical engines to squash that bug. Finally, we'll wrap up with the forced trivialization that ultimately proves the whole conjecture.
Okay, part 1, the Fröberg Conjecture and the search for maximum independence.
So, what are we actually trying to solve here? Well, the Fröberg Conjecture is this massive open problem in commutative algebra. In simple terms, it predicts the exact Hilbert series, which, remember, is really just a handy way of counting the vector space dimensions for each graded component of a quotient ring. The conjecture boldly claims that if you have generic homogeneous polynomials, they are going to remain as linearly independent as mathematically possible. Basically, they'll maximize their vector space dimensions right up until the exact moment the ring components just collapse to zero.
Now, take a look at the exact formula that predicts this behavior. The fraction right there in the middle, that represents the combinatorial maximum we just talked about. But the really crucial part is those brackets with the plus sign at the bottom right. That's the truncation operator. It perfectly captures that combinatorial maximum because it truncates the power series at the very first non-positive coefficient. Literally, it mathematically represents that exact moment of collapse to zero.
Moving on to part 2. The Adelic Langlands map, which acts as our translation engine.
The Adelic Langlands program is honestly brilliant because of how it acts as a universal translator. It takes the super abstract math of the generic homogeneous ideal at the top and maps those graded polynomial degrees onto the flat coordinate lines of the Broussard-Tits tree. Through the geometric Langlands map, this transforms into a Hecke eigensheaf over a Hitchin base, which is just a fancy way of saying we map algebraic lines into geometric quantum states. Finally, it steps down to the local Langlands parameters. So rather than doing some exhausting brute force combinatorial calculation, we're taking algebraic maximality and translating it directly into a physics problem about zero anomaly quantum field stability.
All right, part 3. Let's model an accidental anomaly. Basically, we're going to purposefully inject a bug into the system. Let's pause for a second and play devil's advocate. What happens if a counterexample to Fröberg's conjecture actually exists? Like, what if these generic polynomials somehow accidentally align and form a hidden higher-order relationship, an accidental syzygy, if you will? If that happens, our laws of maximum independence are completely broken. So what would be the physical consequences in our mapped quantum field? Well, if we compare the two states, the contrast is kind of shocking. On the left, we've got our baseline, where the conjecture holds true. The unipotent operators are acting purely off diagonally, and the local Swan conductor, our main diagnostic metric here, just identically collapses to zero. It's completely unramified and stable. But on the right, if we inject that accidental syzygy, all hell breaks loose. The non-generic alignment creates a wildly ramified unipotent vortex. The local Swan conductor spikes completely above zero. The whole system descends into chaos. And this beautifully illustrates how we model that anomaly with the actual math. Over on the left, we've got a parabolic translation block. Notice that local arithmetic parameter, delta p. That parameter is literally measuring the twisting away from our generic baseline. It is our unipotent drift. Now, when we take the matrix logarithm of that block, it directly spits out the nilpotent monodromy matrix you see on the right. So this nilpotent monodromy matrix, let's call it N Fröberg, has some fascinating properties. If you square it, it's actually not zero. But if you cube it, it becomes exactly zero. That highly specific math establishes a 3-tier highest weight filtration chain. In the physical realm, it means our anomalous relation has just injected a severe, highly stratified unipotent vortex right over our local field. The bug is officially in the system. Which brings us to part 4, the fatal phase obstruction, or how the system reacts to the bug. To track this anomaly, we have to look at the local partition factor, and that means unrolling the determinant of our representation space. Because we have that three-tier matrix we just talked about, the local Langlands parameter scales the Fröberg element by the diagonal weights of a three-dimensional triple. You can see that scaling matrix in step 1. We have diagonal p to the 1, 1, and p to the negative 1. When we drop those weights into the determinant in step 2, we unroll the explicit Fröberg local component.
Now, check out step 3, because this is where the massive physical consequence hits. Look at that first factor, 1 minus p to the power of 1 minus s, all to the negative 1. That introduces a glaring, unexpected pole exactly at s equals 1. Because this pole is sitting to the right of the critical edge, it represents a supercritical uncompensated mass state that completely shatters the unitary stability bounds of the local spectrum. This triggers a 5-alarm fire in the universal arithmetic syndrome coordinator. You see, for the global equation to stay balanced, this positive boundary twist requires exact mirror poles to balance it out. But here's the fatal obstruction. The relative tangent bundle of our generic flat affine space is trivial, meaning there are absolutely zero negative geometric classes available to balance this equation. It is a completely uncompensable phase mismatch, a total anomaly blowup.
So, how do we fix it? Part 5. The 4 engines of trivialization. It's time to squash the bug. Engine number 1 is the geometric lens. Here we use the Arithmetic Grothendieck Riemann Roch push forward. Because the ambient space is flat and contractible, the arithmetic Todd class collapses straight to the identity. By applying Stokes' theorem across those non-complex complex coordinates, the entire geometric variation of those non-generic variables is cleanly, completely canceled out. They inject zero net curvature into the physical baseline. The geometry literally just erases them. Engine 2 is the holographic lens, where we map boundary anomalies into the internal Brouhat-Titz tree. Look at the massive formula on screen right now. Specifically, pay attention to that quadratic log divergence term. As we descend into the deep bulk matrix, that spatial resolution amplifier blows up toward infinity. If our accidental syzygy exists, that term suffers fatal quadratic log divergence. It would inject infinite mass density. So, to preserve modularity, the structure violently forces our anomaly parameter delta underscore p to equal 0, no exceptions. The third engine is the spectral lens. This evaluates the continuous scattering spectrum of the Selberg Trace Formula. When we plug our local unipotent factor in, it triggers this explosive spectral residue. You can see it circled right there. Evaluating this along the critical line creates a highly localized, completely divergent spectral resonance. It's continuously pumping infinite word energy into the parabolic cusps, totally violating trace normalization. Once again, it demands the bug be squashed. And when we lay out these 4 engines side by side, the sheer power of this framework is just undeniable. Whether we're looking through the global phase domain, the geometric lens, the holographic boundary bulk matrix, or the spectral derivative, the answer is always the same. The detected anomaly registers as a fatal, uncompensatable divergence. The resolution across every single domain is to forcefully reset the system and quench the anomaly. Which leads us to part 6, the forced trivialization and the final mathematical collapse. Because the automorphic invariance of the universal cosmic partition function is so absolute and rigid, the structural constraints of number theory strictly forbid the anomaly from existing. The system dynamically forces that non-generic translation parameter, delta underscore p, to collapse identically to 0. And when delta p is 0, the nilpotent matrix N Fröberg also becomes 0. The unipotent drift completely vanishes, resetting everything back to our nice, stable ground state. And the final result of all of this is profound. The boundary monodromy is entirely quenched by the global functional equation. This numerical collapse proves, without a doubt, that generic polynomials absolutely cannot accidentally possess anomalous, non-generic relations. By translating a combinatorics counting problem into the realm of quantum fields, we proved that the Hilbert series of a generic ideal has to equal the maximum expected combinatorial bound. The Fröberg conjecture is mathematically proven. I'll leave you with this final, honestly mind-blowing thought from the source material. This proof works because reality's mathematical source code simply will not allow a permanent non-zero spectral scar to exist. It actively self-corrects. It really makes you wonder, if pure math acts as this rigid, self-correcting engine of reality, ruthlessly enforcing balance, what other cosmic bugs is it quietly squashing out there right now, every single second? Thank you so much for joining me on this explainer, and keep questioning the code.